So our next presenter will be Zhang, and her mentor is Elena Vinogradov. And the title of her talk is CEST-Dixon for Human Breast Lesion Characterization at 3 Tesla, a preliminary study. Thank you. Come present to us.
Thank you for your introduction, and good afternoon, everyone. So, mammography is widely used for breast cancer screening. However, it has its own limitations. So recently, MRI is being increasingly used in breast cancer imaging as a supplementary for mammography, both as a screening tool for younger women at higher risk of developing breast cancer and as a problem-solving tool. DCE MRI becomes an indispensable part of the imaging protocol because of its overall high sensitivity. However, it suffers from suboptimum specificity. In addition, the gadolinium-based contrast agent may not suitable for patients with impaired renal function. Because of these limitations, other contrast-free methods such as MR spectroscopy and diffusion-weighted imaging has been explored for breast cancer imaging, either alone or combined with DCE MRI. Another potential method for breast cancer imaging is chemical exchange saturation transfer, or CEST imaging. CEST is a novel method for proton MRI. It can provide molecular level information which reflect the biocomposition of tissues. Hence, we believe by incorporating the CEST imaging into the imaging protocol may lead to technology with improved specificity and prediction value. So in the next 2 slides, I'd like to briefly introduce what CEST is and how we perform CEST imaging. As you can see down here, there are 2 proton pools. One of the pools is water pool. Water is the most abundant molecules in tissues, so it is MRI visible. The other pool, solid pool, it can be amide, amine, or hydroxyl groups in the protein side chains or small molecules. The solid pool is usually in the millimolar range, hence it is MRI invisible due to low concentration. However, if we apply an RF pulse on resonance with the solid pool, the saturated protons in the solid pool can exchange with the protons in the water pool, hence brings down the water signal. By doing so, these MRI invisible solid pool can be indirectly detected by the analyzing the water signal decrease. So in practice, we apply the RF pulses at multiple frequencies and measure the subsequent water signal. This is the so-called Z-spectrum. And based on the Z-spectrum, we can calculate the CEST effect, the so-called MTR symmetry. It is calculated by subtracting the left side from the right side. A big imaging challenge for a successful breast CEST imaging is the presence of large fat content. Fat can lead to lipid artifacts and can confound the CEST contrast. So as you can see in the Z spectrum, the water is in the middle and the solid pools are on the left and the fat is on the right. So when we calculate the MTR symmetry, the MTR symmetry with fat is actually lower than the true MTR symmetry without fat. To remove the fat influence, the CEST-Dixon method is proposed to obtain pure water CEST images in our study. So the imaging sequence is shown down here. The CEST saturation is followed by a 3-point multi-echo Dixon acquisition. Compared with other fat suppression methods such as stir and spear, Dixon method is insensitive to Bezier inhomogeneity. It does not interfere with the saturation pulse train and will not increase in SAR. Another advantage of using Dixon method is that it can provide a Bezier map by itself. Hence, there is no need for a separate Bezier mapping sequence. This saves us scan time. So the goal of our study is to examine the application of CEST-Dixon to breast malignancy and 3T, to compare the CEST signals of normal breast tissues with that of benign and malignancy in different frequency ranges, and to investigate the correlation of CEST signals with breast cancer biomarkers, including estrogen receptor ER and Ki67. So these are the representative CEST images without Dixon and with Dixon. The Z-spectrum and MTR symmetry are averaged in the fibroglandular tissue ROIs in both breasts. So a fat dip can be clearly seen in the Z-spectrum without the Dixon, and it results in a negative MTRN symmetry. And in the water-only Z spectrum and MTRN symmetry, the fat influence has been successfully removed. So the CEST-Dixon sequence has been applied to 5 healthy volunteers and 10 patients prior to biopsy, and later confirmed 8 malignancies and 2 benigns. The 10 patients were stratified into 3 groups: the malignant ER-negative invasive ductal carcinoma group, the malignant ER-positive IDC group, and the benign group. Compared with the ER-positive group, the ER-negative is more aggressive and more likely to recur. And 3 of the patients were excluded from the study because of the tumor type, size, and motion. And all the images were acquired at 3T Philips human scanner. So these are the representative images of a healthy volunteer, a ER-positive IDC patient, and a ER-negative IDC patient. So we can see for the ER-negative IDC patient, it has higher CEST effect compared with the ER-positive and a healthy volunteer. However, for the ER-positive patient, it has similar CEST effect compared with a healthy volunteer. The figure here summarizes the CEST effect for the 4 groups. So for all 3 frequency ranges, we can see the ER-negative group has higher CEST effect than the ER-positive, benign, and normal groups. But for the ER-positive and benign groups, they tend to have a similar CEST effect to the normal group. And of the 3 frequency ranges, the hydroxyl and amine ranges has higher CEST effect in the ER-negative group. But the hydroxyl range has larger difference between the ER-negative group and the other groups. We also correlate the CEST signal with the Ki-67 level in the IDC patient. Ki-67 is a marker of proliferation. The higher the Ki-67 level, the more aggressive the cancer. So as we can see in the figure down here, the MTRN symmetry in all 3 frequency ranges increases as the Ki-67 level increase, but the hydroxyl range has the best fit. To conclude, the CEST-Dixon sequence is robust. Water fat decomposition leads to homogeneous fat removal in water-only images. In the preliminary small group study, the ER-negative malignant tissues display higher CEST signals in all 3 frequency ranges compared with the ER-positive, benign, and normal tissues. Promising preliminary results show that the hydroxyl CEST signal are much higher in the ER-negative than the ER-positive tissues and correlate well with the Ki-67 level, this indicating that the CEST signal may differentiate between more invasive and less invasive breast cancer. At last, I'd like to thank my mentor and everyone in our big research group, and thank you all.
Thank you very much. Questions? We have time for questions. Yes.
I was wondering, very good presentation, by the way. I was wondering what type of coil do you have to use for this, and how do you accommodate for different breast pathology or breast sizes and shapes?
So right now we are using the 16-channel breast coil for both breasts. But right now we scan for 10 patients, but except for the 2 benign cases, the other 8 are 7 of them are mainly invasive ductal carcinoma, and the 1 is invasive mucinous carcinoma. And for the breast shapes, I think we didn't consider for that right now.
That's very exciting work, potentially in this small population if it works out for larger populations. Do you have a hypothesis for why the CEST signal is different for the ER-positive versus ER-negative patients?
So currently we think because ER-negative group is more malignant, so that's why it may has like a more kind of like a such as kind of molecules which is related to this kind of aggressiveness. So these are upregulated because of these are more aggressive tumors, and we see these upregulated molecules may relate it to the aggressiveness.
So it might actually be the intracellular, proteins, amides, all those are at a higher concentration that might be upregulated, and then that transfers a CEST signal, or
Yeah, I think so. Like here, we look at 3 different ranges. So one of them is looking at the amide range, that may relate it to the proteins, but we also look at amine and hydroxyl range, which may relate it to certain kind of molecules, for example, as choline or phosphocholine, such things, which is related to breast cancer.
Mm-hmm.
Shoot, that was great. What kind of information do we have about repeatability with this test?
So currently we are, because right now we are not looking at the reproducibility, but that's what we are going to do in the next step. So in the next step, we are also going to optimize our sequence using longer saturation time as well. So looking at the productivity next time. Okay.
Thank you very much. Thank you, Shu.